In this slide, we're going to look at uncertainties, really just in the time measurement stuff, but even the measurements that I'm taking right now have some uncertainty. When you're measuring a length, it doesn't lend itself to repeated reading because it's the same length that you're measuring again and again. So the uncertainty, then, we have to have a different rule for how we sort of deduce it. And the rule is we use the smallest division in our measuring device. So for example, this meter rule is divided into 1,000 equal sections, one being millimeter. 80.4. 80.4, 0.804 meters. So every time a human being makes a judgment, they're introducing an error to their lab work. So I'm making a judgment about, like, where is the center of this well-shielded pendulum bottle? Where does the line on my ruler meet sort of the other end of the string? And that's another judgment I'm making. And really, this would be like a parallax. It should be looking at eye level straight line. That could also introduce what would be a systematic error, something an error that I could correct for if I was just a little bit more careful. If I stood up on a chair and looked at an eye level. Okay. But then there's going to be random errors. And those scientists just have to acknowledge they're going to be in their experiments. Okay, so we're never going to get perfect. So like with this, we could think about this same sort of idea. What's the absolute uncertainty? What's the percent uncertainty in it? Scientists want to be honest about like how certain we are in our measurements. So if I were to say, well, let me use this rule, like I explained it recording in the slides there, but one way to calculate the absolute uncertainty is half the range of values. We'll have likely a range of values for these products. The biggest minus the smallest, that's the range. Divided into 2, that's the absolute uncertainty in that time. So if I were to do repeat readings with a length, and I said, okay, I just measured it 80.4, and I do it again, I'm like, yep, it's still 80.4. I'm not going to have a range of values. Unless I'm careless, and this time I'm like, oh, look, 81. Well, then I just didn't do a good job the first time. Like, nothing changed the length. So you don't get a range of values by measuring length. Do the same length. You can't have an absolute uncertainty of 0. Every time you can measure, the error is on sort of both sides of the ruler. So if I said, well, the smallest division is a millimeter, but I'm really making a judgment up here and down here, and really, you might say there's more uncertainty in this because you're also making a judgment about where the center of this thing is. Where does the end of this match up with that? You might say there's like 2 millimeters of uncertainty here, and maybe a millimeter or 2 of uncertainty here. Scientists, you look at it and say, well, yeah, it's 80.4, plus or minus 4 millimeters. It might be a little bit more, and that's being, maybe a little bit too conservative and sort of admitting how much error there might be. It's probably much tighter than that, probably like within 2 millimeters. I bet you that's pretty good. I'm trying to be as precise as the instrument allows me to be. And I'm recording this to the millimeter, right? 1/10 of a centimeter. Like that's the millimeters place. All right. So we're not going to worry about like the uncertainty. Now, we're just sort of talking about it right now, but we are going to calculate these uncertainties for speed. And oscillation. Here we go. And remember, you can time any 10. Doesn't have to be the first 10. Right? Count 10 of them, started, count 10. It might be timing right now, I don't know. But I've already got my 10. I got 18.03 seconds. Trial number 2. Sorry, the scientific name is a redo. So, Pretty close. Anybody else collecting data out there? Are your readings pretty close? What did you think? 17.88, and what did you get for the first one? Write it down. Write it down. It's hard to remember all the data we collect. All right, so pretty good. And again, if you're collecting your own data, you just kind of want to say, well, these are pretty close. Our timing looks like we didn't change the length. But yeah, there's some difference. In fact, if there's no difference, just like when we measured the length, you can't have an uncertainty of zero. So if we did it and then just like almost by coincidence, like they just happen to be exactly the same, like there was the range is zero, then we have to use like the smallest division. Yes, like this is accurate to the, I don't know, hundredths of a second. So it's the smallest division in my measuring device is a hundredth of a second. But then you have to sort of like use your reasoning to say, well, but I'm a human being pushing this, and my reaction time is greater than that. And so timing things with a stopwatch sort of has its own rule of reaction time. Like the human reaction time should be captured within this calculation. Like usually you will get a range of values. Right? We already do that one here, although that's really small. Trial number 3. $18.08. All right. Time to calculate. We want to get the average, okay, the average time. Ready? Go. Everybody have it? So we'll stick with this decimal point. It's like 18.05333 repeated, right? But we're going to be consistent always. Like every single one of these is going to be 3 places. Every single one of these is going to be 4. Or to the hundreds. All right, the absolute uncertainty is half the range. How do we get the range? Biggest minus smallest, right? So it's what, 0.05 seconds? Check that in the calculator. No, you don't have to. I trust it. Yeah, that's right. What's half of that though? And how many to calculate? Half of 0.05 is like 0.025 or something? Is that right? 0.025, half the range? It's okay to use a calculator. The range is 0.05, half of that, 0.025, right? Am I doing that correctly in my head? Good. And now we want the percent uncertainty. The percent uncertainty is this. Sorry, viewers. It's this. Absolute uncertainty, which we've just calculated, is half the range of our values, divided by the average measured value, which we got here. Right? So in other words, feel like absolute over measured value. This is why we always want, we want to measure 10 oscillations instead of 5 or instead of 2. Like we could just time 2 oscillations divided by 2, and we get the time of 1 oscillation. Here, the theory is about how long does it take your pendulum to oscillate 1 time? Right? Theory suggests t equals 2 pi root L over g. So we really want this. We would want to time a single oscillation because then our measured value is going to be so low, our percent uncertainty will be really high. We want low percent uncertainty, right? We want to be certain this time. Question? have the percent uncertainty, 0.025 over 18.05 equals times 100. You got what? 0.14% uncertainty. That's pretty good. That's pretty good. Less than 1%, less than a quarter of a percent. All right. And then how are we going to get the time of one oscillation? Divide this number by 10, right? That's the time of 10 oscillations. We want the time of one oscillation. So we're going to take this number, divide it by 10, and then while that's in our calculator, or type it in our calculator rather, we're going to square it. This is squared, that number times itself, right? 3.258. Now, this is what we're plotting, remember, on the y-axis. So we're sort of mindful about the data here in terms of scaling our axis. Will we be able to, sort of get it as precise as the 1,000th place? And maybe not. So we might wow that, but for consistency. Here we go. Seven 71 centimeters is 0.71 meters. We'll put that 0 there because I did read it that precisely. Exactly at 71. 71.0 centimeters. So I want to keep that 0 there. Sorry, I think the timing I should always get fairly wide. Timing oscillation. Trial number 2. .85 that time. Okay. More so we need our third trial here. And remember, it doesn't matter the displacement, like up here, the angular displacement, like 30 degrees, whatever. So just to kind of like a mini experiment to test that idea along the way, you could say, well, let's, like for our next variation of the independent variable, let's just test the one where it's like I barely move it at all. And then the second trial, I'm going to put like over that here. Okay. and we kind of prove to ourselves it shouldn't matter what this angular, amplitude of displacement is, because if we move it further back, it's higher up in Earth's gravity field, it's going to pick up more speed, so its kinetic energy will be greater, it'll have a greater velocity, cover more distance, right? It's got to cover more distance to go all this way, it's going faster. Here, less distance, but going slower. So those things perfectly balance out, if we trust the equation, which probably be on the board here. There's like a mass of the pendulum or angular displacement. The only thing that's at the time, the oscillation and gravity field. Trial number 3. $16.86, really close to that. Should we just keep working through like this throughout the whole table, or should we collect all of our data and then go back? Honestly, I want to keep kind of variable, get all sort of raw data. This is really just analysis stuff that we can do with that here. So it's up to you. Some people think like, oh, it's better to just, hey, while you're at it, if we do it democratically and vote, count the unit votes. If they respond, okay, it's like you can abstain from voting, that's your right. Democracy. Classroom is not a democracy. So, like, we can vote on it. My vote is n plus 1, where n is the number of students voting. But even if there's consensus amongst the students, I can overrule that with my vote, because I have n plus 1 votes. That's democracy. Oh, wait. No, that's an authoritarian dictatorship in my classroom. I reserve the right to change the syllabus at any time for any reason. I want to explain myself. All right. So raise your hand if you want to calculate all this now. E-learners, people watching on YouTube after this has been recorded, comment down below. Be sure to subscribe, hit that like button. All right, so you can pass it, okay? You want to go across here. Ready? I'll raise you. Go. Anybody have it yet? I didn't think so. 7, 8. 7, 8. What's that? Absolute uncertainty. So it's minus smallest, 16.86 minus 0.63 give us 0.230. Okay, just sort of remember how many places supporting this bill. More absolute uncertainty in this. Remember, divide that by the what's absolute, divided by the measured value with repeated readings. The measured value is the average of these. Our measure 16.78. Sort of the best number to use because we collected this stuff. All right, so we 0.23 divided by that, 0.23 divided by 16.78. And again, 10 oscillations takes longer than 1 oscillation. So by measuring a bunch of oscillations, we're increasing the denominator here, thus reducing our percent uncertainty. That's sort of why we want to vary our interval over the biggest range possible. We want to have the highest measured value possible. Times 100. What do you got? Yes. No, I did it on purpose. It'll try and see who's following along and catch that. Counting doesn't say on purpose all the time. Yeah, so we want to go 16.86 minus 16.63 divided by 2 equals first 0.115. I forgot the one out. I was going to correct it. Yeah, and in fact, I was kind of relying on it. Like this top up here, back yesterday, I was rushed out of class. I scribbled the answer down real quick. We were trying to finish the working. I forgot that we were solving for into the denominator. The answer that we came up with here at the end of the first block, there's a reciprocal of that. Let me have that in the notes real quick so we can kind of, that's what I'm thinking about. Oh yeah, speaking of making mistakes all the time, well, I had a backward calculation. Second block, same thing, like 2 hours. So I'm like, oh, we got time for calculations today. Or by the last calculation, your brain turns to mush. It's lunchtime. Like, careless there. Bell rang. Welcome bell. Tell me tomorrow. How it goes sometimes. Who's got that answer from yesterday? Real quick. It was a monster. It was like that's the toughest base units problem you'll ever get, you'll ever see. Something like amps squared per kilogram, something. Who's got that? Anybody? So yeah, it was like per amp squared. Yeah. And then like that, right? Yeah. But remember, like we deduced it, like when we plugged it in, we said, oh, that's what's going to make it work to cancel out. But remember, we were substituting in for epsilon in the denominator. It's like, what are the actual units of epsilon then? Like, because it was in the denominator, it was like amps squared seconds to the fourth per kilogram meter cubed. Right, so when we record our final answer, we have to be mindful that, oh, we were working sort of in the denominator. And so the actual answer is amps squared seconds to the fourth per kilogram per meter cubed, okay? And I don't think I realized that until like I did the same calculation during second block. I'm like, oh, just redo it, show my work so I can kind of go through the working. And because I needed to have more time, I was like thinking, it's like, oh, wait a minute, we're solving the denominator. And then I kind of remembered, like, I don't think I did that when I was, rushed to finish the conclusion during first block, right? That's what's going on. So anyway, yes, thanks. Minutes. All right, so we want this 1.115 divided by 16.78 times 100%. That gives us 0.9%. Time for one oscillation is divided by 10, so 1.78. 1.678 squared. 2.816. Put your own data table, pause the video once I display it, fill in your journal, and then play it again. Just gotta keep moving here. Not too much time spent right in class. Point 608. All right, trial one, we're going to release from here at an amplitude of about 5 degrees. Got 15.36. Now, you might criticize this and say, wait a minute, why are you changing another variable? You shouldn't do that in science, right? Like only manipulate one independent variable, that's the length of the string here. So now like you're changing the amplitude. We're just kind of doing it as an exploration because we kind of already know this physics very well. Like this is the same experiment Isaac Newton did 400 years ago to figure this conclusion out. Like same Earth, you know, that we're standing on today. So because we kind of already know that theory is pretty well established, we're kind of exploring that idea that it shouldn't matter what this displacement is, but it is indeed like changing another variable. And if like we were exploring this for the first time, like doing an experiment to figure out, you know, these relationships in nature, we would want to be very careful, like not change the mass of this, everything else exactly the same, right? Controlling every other variable besides the independent variable. And then you can measure as many dependent variables as you want, right? Like we're just measuring time, but we can measure other things too, you know, like have more sensitive equipment, like how does the air get displaced? You know, so you can measure as many dependent variables as you want, but only change one independent at a time. So I'm gonna go here to the violate my own rule right there and just explore this idea that it should be about the same. Okay, that the time period of oscillation doesn't matter based on the initial angular displacement. So here we go. Final words. I get 15.66. And now you might say, change, you know, it goes a little bit slower, you know, it takes more time. But really, we kind of already know that we expect these slight differences, right? That's sort of the whole idea here with uncertainties. Like, that's pretty good, right? It's like, yeah, it didn't matter. Like, it wasn't so different that we question, like, oh, maybe there is. But you could maybe design an experiment to really sort of verify that concept to yourself. You know, test a whole bunch of different stuff. Kind of prove to you, yeah, it doesn't matter. Right? It doesn't matter. Now, eventually it does matter. Okay, I've already do this. The other slack in the line, that ruins it. 2 pi here, pi, you're looking for a circle, okay? And we're sort of sticking out an arc of a larger, you know, circle that way. We need to do that. Like, what's the period of this oscillation? Conical pendulum. Anybody know the conical pendulum? We'll study that in Pig's Fly. Example. So the conical pendulum. Conical pendulum, right? You could do this lab with that. You could do the period of oscillation of a conical pendulum. The ones that take a circle that forces it. Okay? With that conical pendulum, there's a force of tension. Like the string is like this. The pig is like this. The pig has weight because the pig has mass, right? And weight always acts straight down. So you say, okay, that pig has weight mg. There's tension, right? The force of tension in this string. Well, if the pig isn't accelerating in the y direction, that pig didn't start falling down or flying up, then this weight force must be balanced by what? A component of the force of tension in the y direction. So like there's tension in the string, but there's a component that acts straight up that balances the weight of the pig. And so what does this component do? The force of tension in the x direction. It's acting towards the center of that circle that it's sweeping out. So that force is the necessary force to keep the object moving in a circle. Objects don't move in circles on their own in this universe of ours. Some force is required to keep them moving in a circle because it's the first law of motion, right, that we're studying here. Object in motion remains in motion in a straight line. So this pig should just fly off in a direction tangential to the circle. The fact that it doesn't, at every moment, there's this centripetal, this center-seeking force provided by the x component of tension that keeps moving in a circle. In astronomy, this is like gravity between the sun and the earth that keeps the earth moving in a circle. So like the physics we understand with a flying pig here in my lab, we can apply all over the universe. And like that's the power of physics. That's why it's so awesome. Well, you know, but you can see like we're building the foundation here to do more interesting analysis like this. Like tether ball, you know, you do a tether ball lab, go out there and calculate these components. Digress from my lab work. I could just fly today, you know. Set down and things fly. Didn't really fly. Number 3. That's exactly the same. Somehow we're getting the value to that. So, what they're doing is experiment, we end up getting that one line where it's like, oh, let all of you have a second there on, or and kind of see what's happening in the at the time, are getting less and less as we make it order, then the value we're dividing by smaller numbers, so we would expect these. All right, let's work through here. Tension is that a stopwatch is also a factor. I guess that's I always thought about that with a remote control. It's also a telephone. Buttons on it. Watch this on like, oh, we want that turn on. That's like, and now everybody has like a remote control on it. 15.36. I get for an average time 15.56. And then 0.66 minus 15.36 is 0.3. So 0.3 is the range. And then divide it by 2, right? 0.15. So still the absolute uncertainties of the increase. Remember, as we decrease the length here, we kind of expect that. And we'll take this absolute uncertainty divided by the average time. 0.56 times 100% and 0.96%. So it's still under 1% uncertainty. That's pretty good. One oscillation, 1.556. 1.556 squared. I'm just going to my head. It's on the camera. Yeah, 2.42. That's about there. 0.421. All right. You guys watched the last time we did a Pendulum Lab. You know, all that footage is on YouTube. You know, it's very interactive. For example, when we vary the independent variable, we already know how exciting that is. There we go. judgment in physics lab on lab day. Watching the pendulum swing back and forth, writing down numbers, calculating averages. I think that much better. That's a lot. 50, 20, 50.9. That's pretty good there. Varies by about 10 centimeters at a time. 50.9. Before I start that, everybody following along at home, pause the video, fill in your own data table. Here we go. $14.37. Oh, sorry. 14. Let me know if I need to look at it. Trial number 2 for me anyway. Oscillation. All right, I got 14.3. Trial number 3. Looks like we're almost like halfway done with the lab. We're halfway maybe by now. I got 14.26 on that trial. All right, so let's calculate the average time of oscillation. 14.7 plus 14.3 plus 14.26, 42.93 divided by 3 equals 14.31. $14.37. It was a 0.11, right? 0.11 divided by 2. 0.055. So less than these two. That can happen, right? So even if there was a violation in this trend, then I'd be kind of worried. Like we'd have a data point that doesn't quite match the rest of the trend line. But here it's just kind of like, hey, yeah, we did, a better job with our time. So that's the absolute uncertainty, but it does almost come by the measure value, 14.31 times 100, 0.3. I don't know if I second best data point in terms of that. Time for one oscillation is 1.4. And again, that's kind of like what 10 oscillations instead of like 1 at 12. Then we have an even higher measured value. 14. That's going to pass easy. 10 oscillations. It's easy to calculate. If we find 20 oscillations, 500. On the max, at least, we are now. Point 0. snapshot of the data table, the rest of it, up to now. Cart. Thought the variation between 0.608 meters and 0.509 meters was awesome. Just wait until we vary the independent variable right now. Got it. .436 meters. Let's measure the dependent variable. .13.39 is what I got. Probably more oscillation than anybody's typically their own. Trial number 2. .12.92. Trial number 3. .13.14. And if you're getting your own time data, then this is going to be a little bit different. It's going to be roughly about we're all observing. But it's good practice to collect your own data and kind of work these calculations. But when I first learning, I understand it's like, well, let me just make some of it before I put my confidence. To copy this data down today, conduct this experiment for yourself or somebody of it on your own time, and analyze both sets of data. Um, 13.15 I get for an average. We do 13.39 minus 12.92. 0.47 and then divided by 2 or divided by half. That's the worst one at 0.235. I get for the absolute uncertainty. The absolute uncertainty here in T is really in the same units, right? Like we're uncertain in 0.23 seconds. So that perhaps absolute also pretty 0.235 over 13.15, right? Absolute over measured value times 100%, 1.79% uncertainty. Larger than everything else, but still not too bad. 102% certainty. Good. More here. 1.315 and 1.315 squared 1.7. So remember, you want to calculate t squared in this column here. That's what we're going to ultimately plot on our y-axis, right? Against the length value. Because it's easier to work with t squared against L than t against the square root of L. You could plot it that way if you want. Two more variations. Let's get one right. There. That's the spot. Thought that was loud. Comment down below. $31.7. 0.317. Yellow against black, darkest contrast. So street signs, okay. Speed limits, white background, it's not that important, but like fields, okay. So that stands out the most. So that's why I'm using yellow chalk today. And for everybody in the know, Hagoromo chalk. Look it up. Don't know about Hagoromo chalk, but you will. All right. Remind me tomorrow along with the flying pig. Okay, Hagoromo chalk, flying pig on tomorrow. Trial number 1. Redo. $11.10. Trial 2. $11.14. Flip that. $11.06 for me. Calculate the average. 11.1 plus 11.14 plus 11.06 equals 33.3 divided by 3. Can we do that in our head? 11.1, right? Sometimes you get little bonus surprises in the middle of your, analysis. Oh yeah, you're gonna have fun varying the independent variable, but then you come up with something like this. Oh, like 33.3 divided by 3. How awesome is that? I can feel the excitement in the room. All right, let's get the absolute certainty. .04. Everybody following along? Divided by 11.1 times 100. 0.36% uncertainty in that. 1.110. 1.11 squared. 1.23. All right, so the data table up to this point looks like that. All right, one more variation of the independent variable. Kind of like, it's going to be awesome. The last one. The last one next week. Go. Now, before I measure this, I want to point out, why not this one? Like, vary it over the biggest range possible. I really think our results suffer you know, like maybe we check that one, and then it's like we have a trend, and then when we plot that one, it seems to play off, and we're like, an anomalous point. Maybe there's something about that physics, like the fact that we sort of stop the string with like the way this bob is, you know, maybe that's like sometimes the discrepancies in the data we collect can reveal kind of something interesting, or, you know, interested in it. I don't know why we would be in this case, but maybe they, you know, I think that's about one here. We gotta hurry up and collect this because the pendulum bob is no longer shielded by the plexiglass barrier. I'm kind of worried about it. 1.7. I did like 60.8, 50.9, 20.7, 0.4. There's the dependent variable. Two, trial number 2. Nine point oh four. Nine point one one. 9.11 plus 9.04 plus 9.02 equals 27.17 divided by 3. 9.06. And then we got 9.11 minus 9.02 is 29. Yep, divided by 2. 0.045. I clean up the data table, make sure everything is like this. 1.5, 1.50, 4, I got an absolute uncertainty divided by my average value, 9.06 times 100%, 0.4. I guess I would round up. 0.5%. Divided by 10, so we got what? 0.906. And 0.906 squared, 0.1. And that completes the data collection for our second pendulum lab, pendulum lab number 2, we'll call it. And because theory suggests that the time of a simple oscillation is equal to 2 times pi times the square root of the length of the pendulum string meters over local G reverse gravity field. Organize this equation, plot a graph of time squared against L. Plot this data where the x coordinates are the length. The x coordinates are the length, the y coordinates are the t squared, right? So we're plotting t squared equals 4 pi squared over g against L, right? So that's your y and that's your x. Plot the data, draw a trend line through it. 1 or 2 points to calculate the slope, and then the slope should be equal to this term, 4 pi squared over g. So you'll set the slope equal to that and then solve for g. That will be your claim. G equals whatever. And we'll compare that to the last pendulum. Well, even though this was a lengthier process in terms of the data collection, we get better results if we really by doing repeated trials and good practice to honest in our data collection to say, like, here's how certain we are even about this. So that's just sort of the rule that we agree upon as scientists. Take half the range of the values, and that's the absolute uncertainty, divided by the measured value to get the percent uncertainty. We can reduce the percent uncertainty, which we want, by having higher measured values. I mentioned, I think, gravity waves, maybe not in this class. We were looking at a quantity called strain. Okay, and a few years ago, they measured gravity waves for the first time. They were measuring strain, which is sort of the compression of space-time itself. And in order to measure that, because gravity waves have such a small effect, they had to have the laser beam is like 4 kilometers long, and it sort of bounces off of a mirror and comes back. And as a gravity wave passes by, the strain of sort of space-time compresses, and the timing of that laser changes by a little bit. But in order to even see that small change, you need to compare it to a really big sort of value. So anyway, that was some groundbreaking work. There's like 40 years in the making, and the people that started that experiment shared the Nobel Prize. All right, I'll do it for lab day. You'll want, oh wait, we got to do a